Dear students, in this video we will discuss few other operators. So here first operator is the shift operator and denoted by capital E. Capital E. So when you operate this operator on a function f of x, then this will shift. This will shift with the distance h. So E of f of x is nothing but, suppose here shift the distance is h, so f of x plus h. So E of f of x is nothing but the value of the f shifted by the distance h, so f at x plus h. If you again apply this, so that means twice shifted. So now E, this can be rewritten as E f of x, but E of f of x is nothing but f of x plus h. Again apply on shift operator here. So again you have to shift this value by a distance h, so that's why f of x plus 2h. And so if you apply this shift operator n times, then f of x plus nh. En f of x is nothing but f x plus nh. Fine. Now inverse shift operator, we are moving in the reverse direction. So E minus n f of x is nothing but f of x minus h. We are moving in the reverse direction, so shifted in backward direction with a distance of h. Similarly, if you are applying again E minus 2 f of x, this can be rewritten as E minus 1 f of x, but E minus 1 f of x is nothing but f of x minus h. Again apply inverse shift operator, so this is nothing but f of x minus 2h. So if you are applying n times this operator E minus n f of x, then this will be nothing but f of x minus nh. Fine. Now averaging operator. Averaging operator is denoted by this mu. So mu of f of x is nothing but the value of the function at x plus h by 2 plus f of x minus h by 2 divided by 2. So this is the meaning. That means here, if suppose we have this, here is x, here is x plus h by 2, here is x minus h by 2. So value is f of x minus h by 2, here is the f of x, here is f of x plus h by 2. Then according to this, if you want to find out the average value of f of x, then this is nothing but the value at this place plus value at f of x minus h by 2 divided by 2. So this will be the average operator. Identity operator is nothing but just deals like is nothing but identity. So identity operator, when operated on f of x, this will give you same function f of x, or in some books this is denoted by 1. So 1 f of x is nothing but f of x. So this is the identity operator. Now here we have few relationship between different operators. First relationship is delta is equals to E minus 1. Second relation is that nabla is equals to 1 minus inverse shift operator. Third is nothing but central difference, that means Kronecker delta is equals to E half minus e raised to the power minus half. Fourth one is mu is equals to 1 by 2 e raised to the power half plus e raised to the power minus half. Fifth one is delta is equal to E nabla is equals to nabla E is equals to Kronecker delta e raised to the power half. And last is E is equals to e raised to the power hd, where d represents the differential operator. So this is the relationship. Now we will establish these results one by one. So here is the first one. So here, since we want to find out the relationship between delta and E minus 1, so here this delta is operated on some function f of x, and by the definition this is the forward difference operator, so its value is nothing but f of x plus h minus f of x. We have already discussed this in previous video. So this is equal to this, but this can be written in terms of shift operator as E f of x, and with the help of identity operator this can be written as 1 f of x. So we can take E minus 1 common and f of x here. So when you compare left hand side and right hand side, this is valid for all f of x, that's why operator will be same. So delta is equals to E minus 1. So this is the proof of the first part. Similarly, second part. In the second part, Now we will apply nabla operator on f of x, which is the backward difference operator. So this is nothing but f of x minus h. This is the definition of the backward difference operator. Now here we will apply the identity operator, so 1 f of x, minus here we can apply inverse shift operator, so e minus 1 f of x. When you combine these two, so 1 minus e minus 1 f of x, and this is combined because they are linear operators actually. So they are linear operators, so that's why we can rewrite this as this. When you compare left hand side and right hand side, so we can compare the operators also. So that's why nabla is equals to 1 minus e minus 1. Fine. Now third relationship. Here is Kronecker delta f of x is equals to, by the definition, this is nothing but f of x plus h by 2 minus f of x minus h by 2. This is the central difference. Now using inverse shift operator here, because here you can see that if you are applying shift operator, then generally we have this relation, e of f of x is nothing but f of x plus h. That means the coefficient is 1 here, that's why its power is 1. Here is 1, that's why 1. If power is half, so we have to take half, that's why this is written here. So this is nothing but, since here the coefficient is half, coefficient of h is half, that's why e raised to the power half f of x, minus similarly here this can be rewritten in terms of inverse shift operator. So coefficient of h is minus half, that's why e raised to the power minus half f of x. When you combine these two, so this can be rewritten as this. When you compare left and right hand side, so this is Kronecker delta is equal to e half minus e minus 1 half. So this is the proof of the third part. Now the fourth part. Here we are taking the average. So mu of f of x is nothing but 1 by 2 f of x plus h by 2 plus f of x minus h by 2. This is by the definition of the average operator. So again 1 by 2, this can be rewritten in terms of shift operator as e raised to the power half f of x, because the coefficient is half, that's why power is half, plus here the coefficient is minus half, so e raised to the power minus half f of x. When you combine these two, so this can be rewritten as this. And when you compare left hand side and right hand side, so this can be written as mu is equals to half e raised to the power half plus e raised to the power minus half. Fine. So this is the proof of the fourth part. Now the fifth part. In fifth part, we want to prove this. So what we will do, we will take this part and we will show that this is equal to delta. Let's see here. So e nabla f of x can be rewritten as e nabla f of x, but nabla f of x is nothing but the backward operator, that's why this can be rewritten as e f of x minus h. Now apply this shift operator here, so this is shifted by the distance h, because here power is 1, so that's why f of x plus h, minus when you apply this here again shift with the distance h, so this is nothing but this will be f of x now. So this is, but according to the forward difference operator, this is nothing but delta f of x. So when you compare these two, so this is e nabla is equal to delta. Fine. So now we have proved that this e nabla is equal to delta. Similarly, we will show that this nabla e is equals to delta, and in the last we will show that this is equal to this. So now we will show that this nabla e is equal f of x is equal to delta. So how? So we can rewrite this as nabla e of f of x, but e of f of x is a shift operator, so that's why this is shifted by the distance h, so f of x plus h. Now apply the nabla operator. So this is nothing but the current value, which is f of x plus h, minus its previous value, so minus f of x, which is nothing but the shift operator, so delta f of x, and that's why when you compare, so we will get this result. Now here the last part of this one is Kronecker delta e raised to the power half f of x, so delta e raised to the power half of x. So now apply shift operator with power half, so that's why shifted by the distance h by 2, because power is half, so that's why delta f of x plus h by 2. Now apply the central difference. So central difference means add half, so when you are adding h by 2 here, then this will be f of x plus h, minus subtract half, So that's why you are getting f of x here. Again, this is nothing but the forward difference, delta f of x. When you compare, so you will get this result. So from these two you can see that this is equal to delta, this is equal to delta, this is equal to delta. That's why they are equal and the value is delta. So this is written here. Now the last part of this relationship, here e of f of x is equals to this. E of f of x is equals to nothing but, by the definition of the shift operator, this is equal to f of x plus h. Now apply Taylor series. So this is expanded about h with distance h. So f of x plus h, first derivative of x, plus h square by factorial 2, second derivative of x, plus and so on. Fine. And since we know that this can be rewritten as d of f of x, here d represents the derivative. Derivative means d by dx. D is nothing but d by dx. Here d is nothing but d by dx. Fine. So d by dx of f of x plus h square by 2. This is the second derivative, so d2 f of x and so on. And since this can be rewritten as identity with the help of identity operator as 1, so now you can take f of x common here, so we can operate this, because this is derivative is nothing but a linear operator also. So 1 plus hd plus h square d square by factorial 2 and so f of x. So when you compare left hand side and right hand side, so e is equals to this operator. But this is nothing but the exponential series, e raised to the power hd f of x. Fine. This can be rewritten as e raised to the power hd f of x. Now when you compare, so e is equals to e raised to the power hd. So this is the relationship. So if you will see the first relation, which is nothing but this. If you will see the first relation, delta is equal to e minus, from here e will be 1 plus delta. E is equal to, but according to e is e raised to the power. So when you compare, so we will get this relationship. So this is the note point. In the next video, we will take few examples based on these relationships. Thank you.